Fermi questions are questions of estimation. They're named after the physicist Enrico Fermi, who is famous for making very good approximate calculations given very little data. For example, he estimated the strength of the atomic bomb detonated in the Trinity test based on the distance traveled by pieces of paper dropped from his hand during the blast. Now, you can argue that standing so near an atomic bomb detonation was not the wisest thing to do, but it was a very clever calculation. We practice Fermi questions to practice two distinct skills: dimensional analysis, which you can think of as unit conversion, and making reasonable assumptions. These assumptions must be clearly identified in your solutions. One classic question, attributed to Enrico Fermi himself when he taught at the University of Chicago, is, how many piano tuners are there working in Chicago? There are many possible assumptions that you could make that would lead you to a reasonable answer. Here's one set. There are approximately 5 million people living in the city of Chicago. On average, there are about 2 persons in each household in Chicago. Some families might have a couple of kids, some people might live alone. On average, 2 persons per household. Roughly 5%, maybe, or 1 household in 20 has a piano that is tuned regularly. Pianos that are tuned regularly are tuned on average about once per year. It takes a piano tuner about 2 hours to tune a piano, including travel time to and from the household. And let's say each piano tuner works full-time, 8 hours in a day, 5 days in a week, and 50 weeks in a year. Now, how can we turn those assumptions into a number? We're going to convert units of people to units of piano tuners by multiplying by conversion factors. Let's start with those 5 million people and turn them into households. We multiply by our conversion factor, people to households. Since we want to cancel out people, people goes on the bottom, the denominator of our conversion factor, and we're left with households. We can then turn households into pianos. Households goes on the bottom in the denominator of our conversion factor. We're left with pianos. Continue until we have an estimate of 125 tuners. That sounds like a curiously exact number. And remember, these are not the only set of assumptions that could have been made. But any set of reasonable assumptions should arrive at an answer of, if not 125, of the same order of magnitude. At least the exponent on the answer, if the answer were written in scientific notation, would be the same. Fermi estimates are therefore usually given to only one significant digit, or even just the order of magnitude. For example, our answer of 125 would be written as 100 tuners, or 10 to the power of 2 tuners. Incidentally, Enrico Fermi's estimate of the Trinity detonation was 10 kilotons of TNT. A more precise calculation would be closer to 18 kilotons of TNT. With just his strips of paper, he was within a factor of 2 and certainly of the right order of magnitude. Now, Fermi estimates provide a useful check on results. Where the complexity of a precise calculation might obscure a large error, the simplicity of Fermi calculations makes them far less susceptible to such mistakes. Here's an example. Let's say you have a computer program designed to calculate the mass of a black hole by observing the Doppler shifts in the spectrum of its companion star as it orbits. Now, let's say this computer program has a bug and keeps giving you a not a number error. How will you know when you've likely correctly fixed the bug? When you get a number of 10 to the power of 21 kilograms, 10 to the power of 31 kilograms, 10 to the power of 41 kilograms? What's a reasonable answer? And realize that these 10 to the power of 21, 10 to the power of 31, 10 to the power of 41 are not all pretty close. These numbers differ by factors of 10 to the power of 10 or 10 billion. You'd be annoyed if you won a $10 billion lottery and somebody showed up at your door to give you your winnings and handed you a loonie and said, meh, pretty close. Now, let's see how pretty close you can get on this practice question. This question will require more than just unit conversion. It will also require the use of some equations, which depends on which strategy, which solution you choose. Estimate the mass of the Earth without looking up any information. Pause the video and take a couple of minutes to do this. Now, while there's only one answer, there are many different solutions that will get you to that answer. You might have chosen a different one than the one shown here. It is, for example, possible to estimate the mass of the Earth from the position and period of the orbit of the International Space Station. The following solution uses the formula density equals mass over volume, solve for mass, density times volume. I'm going to estimate the mass, estimate the density, and estimate the volume. Now, density. I know without looking it up that the density of water is 1 gram per cubic centimeter. Thinking about holding a full bottle of water and holding a light rock about the same size, I think light rocks are probably about 2 to 3 times that. Now, the Earth is not entirely light rock. I know that the interior core is solid metal. Well, I also know that a nickel, solid metal, is about 5 grams. It's probably, if I think about chopping it up and fitting it into a little cubic centimeter box, about half a cubic centimeter. So I'm going to estimate that the density of solid metal is about 5 divided by 0.5 or 10 grams per cubic centimeter. So we'll assume that the Earth is a mix of solid metal in the core and lighter rocks in the crust, averaging out to be about 5 grams per cubic centimeter. Note the twiddle in front of that 5. It could be 4, it could be 6, but it's probably of the right order of magnitude. Now, do remember to convert to SI units. 5 grams per cubic centimeter should be turned into some number of kilograms per cubic meter. Remember, when you convert cubic centimeters to cubic meters to cube the conversion factor between centimeters and meters, you should wind up with 5,000 kilograms per cubic meter. Volume. Now, my formula for the volume of a sphere, 4/3 pi r cubed, requires me to first have some idea what the radius is. Now, let's say I haven't been teaching physics for long enough that I know the radius of the Earth off the top of my head. Let's come up with some estimate of the radius based on everyday experience. Now, I don't normally dig down into the center of the planet, but I do travel around the planet, and I know that it's about 4,000 kilometers from Hamilton to Vancouver, which is 3 time zones away. Now, assuming that time zones across the equator are, let's say, about 25% wider, I can turn a circumference of 24 time zones into a circumference of 40,000 kilometers, or 4 times 10 to the power of 7 meters. I can then use that circumference to find my radius, plug that radius into my formula for volume, and come up with an estimate of the volume of 1 times 10 to the power of 21 cubic meters. We hope that that's the right order of magnitude. And remember, since we only want the right order of magnitude, we don't really need a calculator to come up with these numbers. All we really need to do is a little bit of mental math. We can estimate as we go along. For example, we can use 3 for pi. Our calculation 4 times 10 to the power of 7 meters divided by 2 pi becomes divided by 6. So we have about 2/3 times 10 to the power of 7 meters, or about 6.5 times 10 to the power of 6 meters. To cube 6.5 times 10 to the power of 6 meters, well, let's cube that 10 to the power of 6, turn it into 10 to the power of 18. To cube 6.5, well, 6 cubed is about a little more than 200. 7 cubed is between 300 and 400. So we'll say that 6.5 is a little shy of 300. Multiply that 300 by 4, because remember our 3 and our pi cancel out. We're going to end up with some number that's close to 1,000, 10 to the power of 3. That 10 to the power of 3 times that 10 to the power of 18 gives me 10 to the power of 21 cubic meters. So my estimate for the mass, multiplying the density times the volume, works out to be 5 times 10 to the power of 24 kilograms. How close am I? Let's ask Google. Google says that the mass of the Earth is 5.972 times 10 to the power of 24 kilograms. It's that 10 to the power of 24 that's important. I am the right order of magnitude, and I hope your own solution was as well. If not, well, we're going to get lots more practice.